So this is the third video on Excel, and I thought this time I would start with looking at discrete data, and discrete data where you are comparing two situations. So if you are comparing two situations, for instance, two different pHs with the yeast, or you might be comparing two different ecosystems or two sections of an ecosystem, this little section is for you. Your data should be set up something like this, and if you're not sure how to set up your initial spreadsheet, can I refer you to an earlier video, the Senior Student Experiment, Discrete Data Part A. So this is Part B. Once you have got your data table set up, remembering that over here I have got my replicates, my number of repetitions, and for this scenario where I was comparing the number of damselfly larvae found in still water as opposed to fast flowing water in emerald lakes, I've got the number of damselfly larvae found in each still water replicate here, and the number of damselfly larvae found in fast flowing water replicates here. Now because I'm comparing them, I want to do the t-test. So the t-test means I'm going to have to use the data analysis toopak. So I'm going to go up here to data and click on data, and right over here at the edge you can see I've got data analysis. Now I'm going to click on that, and it brings up this lovely little screen which allows me to choose a number of things. Now if you don't recognize it, don't even bother going there. And remember, you need to scroll down because we want to do a t-test. So here we've got the t-tests, a t-test for paired two sample for means, and we have got a t-test two sample assuming equal variances. Now the t-test that you're going to choose is going to depend on your conditions. So if I decide that the fast flowing water and the still water that I got my samples from were from completely different sections of emerald lakes, and therefore this sample had no effect on that sample, I've got two completely independent samples, then I am going to do a two sample assuming equal variances. So I'm going to do that first. I'm going to click OK. And it took a little while, but there it is. Now once you get this little square up, it's asking you, what should I put in here as my range, my variable 1 and my variable 2, what should I put in there? These little arrows, you just click on them and it pops you out of this dialog box and allows you to input stuff. So my variable 1 is the larvae in still water. You click on that, and I'm just going to highlight those squares, and you can see that it's listed them there. If I click on my arrow to take me back in, you can see that I have now chosen those squares. My second range is this column here. Again, I'm going to click to go out, and I'm going to highlight those, and I've now input those. You don't need to worry about anything else. It should automatically be set up. Remember, I'm not teaching you statistics, I'm just helping you get through the statistics for biology. We do need an output range. The output range is Excel saying, where do you want me to put this? And that really is up to you. So click output range, click on the little arrow so that you can pop out again. I'm just going to put it here. There, I've got it there. Go back into my dialog box and I click OK, and here I have got a table that Excel has calculated for me. I'm going to make these slightly bigger so that you can read what they say. Remember that variable 1 is the larvae in still water, and it's a good idea to change that heading so that your headings are correct. And variable 2 was the number of larvae in fast-flowing water. And I'm going to wrap that so that it looks nice and neat as well. Okay, I've got the two means here, which means I don't have to calculate them. I can just copy those, Control C, and I can pop them in there. I have my two means so that later on, if I want to, I can generate a graph. Now, the bit that's important here, besides the means, are not all these other numbers for you guys at the moment. We want to be able to say, what is the probability that there's a significant difference between these two samples? So we're going to choose the P2 tail. Just remember P2 tail. You don't have to worry about any of the others. You don't even need to know what it means. If you study statistics later, you can have the joy of understanding all that. I'm going to make that highlighted so you can see it. And here I've got my p-value. P bracket t less than or equal to t, 2 tail is 0.134, and a whole lot of other numbers which are not so important. We're going to come back to that p-value in a little while. Before we talk about the p-value, I just want to look at the other scenario. So imagine that my fast flowing water was actually flowing into the still water where I was doing my sampling. So I'm sampling water here, and this water is flowing into this water here that I'm also sampling. It's highly likely that this sample could have an effect on that sample, in which case these are not totally independent of each other, because the one could be affecting the other. So if one of your samples could be affecting the other, then you want to use the paired t-test. So let's just do that as well, just so that you can see what happens. Again, we're going to go to the data. We're going to go to data analysis. But this time we want a paired t-test. T-test paired two samples for means. I need to put in my input range. And my second variable range. Have it there. Just want to chat a little bit about this alpha value. That alpha value is 0.05, and if you've been paying attention to the notes in the statistics book, that is what our p-value looks like as well. So don't change that, just always make sure that your alpha stays at 0.05. Now I need to choose an output place and pop it over there, and there we go. You will notice, while I quickly change these columns, you'll notice that the mean is the same. That's because it's the mean. The mean is not going to change depending on whether they are samples that are independent of each other or samples that are dependent on each other. But you will notice that the P2 tail is slightly different. Let's highlight that one so we can see it. It's slightly different. This one was 0.138, which rounds off to 0.14, and this one is 0.141, which rounds off to 0.14. So if you make a mistake and you choose the wrong one, it's actually not going to affect your discussion terribly much. And I guess I'm telling you this just so that you can worry a little bit less. Alright, let's get to these p-values. So the p-value is going to tell you whether there's a statistically significant difference between the two groups. And what we have to remember is if the p-value is less than 0.5, 0.05, then there is a significant difference between the two groups. And remember that when we talk about significant difference, we mean in terms of statistics. So we don't have to say statistically significant, we can just say significant difference. If the p-value is greater than or equal to 0.05, then there is no significant difference between the two groups. So how do we interpret this? For this sample in the still water, we've got an average of 1.6 damselfly larvae. We can't really have 0.6, so we would have to round that up to 2. And in this sample here, we've got an average of 0.8 damselfly larvae. So we would be inclined to say that there are more damselfly larvae in still water than found in fast-flowing water. However, because our p-value is greater than 0.05, we have to say there is no significant difference between the two. And we cannot actually say that you will find more damselfly larvae in still water than in fast-flowing water. We're nearly done. So what could we actually write for this investigation? Let's start with the statistical interpretation. The statistical interpretation is that there is no significant difference no significant difference. Now we have to justify that, so we put in brackets P, and we write down what the p-value is. I am going to use this one here, so this p-value there, P equals 0.14. I'm going to round it up. And we need to say which is greater than 0.05. We have now justified why we're saying there is no significant difference. So now our biological conclusion, or our biological explanation of the data is, therefore, and there we have it. So we've got a statistical conclusion and we've got a biological conclusion linked together, and we're done.